We talk about an ideal gas a lot at the beginning of the chapter, but does ideal gas really exist? Actually, an ideal gas is a hypothetical gas that obeys the gas law and the kinetic molecular theory. The kinetic molecular theory states the following. First, the volume of the gas are negligible. This is because the molecules of the gas, the particles of the gas, is extremely small compared to the volume of the container. Second, the gas are frequently colliding with each other and also with the walls of container. Third, there is no net loss or gain of kinetic energy when the particles collide because the collision are completely elastic. Fourth, the intermolecular forces between gas particles are negligible and the total kinetic energy is constant, so there is no intermolecular attraction or repulsion at all. Fifth, the average kinetic energy is directly proportional to the absolute temperature in Kelvin. Real gas is actually a gas that deviates from the ideal behavior. So it does not obey the gas law, the volume of gas particles are significant, and also the intermolecular forces between gas particles are significant. So from the ideal gas equation, which is the PV is equals to nRT, okay, for each 1 moles of the gas, okay, the product of the PV over RT is always equals to 1. So if you look at this graph, okay, we have the y-axis, which is the product of the PV over RT, and the x-axis, the pressure in ATM, okay. So for ideal gas, okay, for ideal gas, the product of the PV over RT is 1.0 at all pressure, at any pressure. If you look at the graph, at very high pressure, the product of the PV over RT is bigger than 1. So we have a positive deviation here. This is due to the particle volume. Okay, at low pressure, okay, so the volume of the free space, okay, volume of the free space is about the same as the volume of the container because the size of gas particles are very small, so we can neglect the volume of the gas occupied in the container. But as the external pressure increases, okay, if we increase the external pressure here, we can see that the volume of the gas becomes significant because the free space in the container is smaller than the volume of the container itself. The volume in the PV over RT here is actually the volume of the container. So since the volume available for the gas particles, the free volume here is smaller than the volume of the container, okay, that makes the product of the PV over RT bigger than 1. At moderate high pressure, we will get a negative deviation where the product of the PV over RT is less than 1. This is due to the interparticle attraction. At lower external pressure, the spaces between the gas particles are so large. So, the interparticle attraction between the gas particles is negligible. Okay, kita boleh abaikan dia punya attraction. Okay, but as the external pressure increases, okay, at moderate high external pressure, the particles will get closer to each other. So, we cannot neglect the attraction between the particles, okay, if the spaces is very small. Okay, so the chance for the gas particles to collide with the walls of container will decreases and it will make the pressure of the gas becomes lower. So since the pressure of the gas is lower, that's why the product of the PV over RT is less than 1. Gases with strong intermolecular forces, will show a greater deviation from ideal gas behavior. So we have CH4, N2 and H2 and also the ammonia, the NH3 here. So since ammonia has strong hydrogen bond between its molecule, we can see here ammonia give a large deviation from the ideal gas behavior compared to CH4, N2 and H2. So hydrogen has a smaller deviation compared to other gases because the intermolecular forces between hydrogen gas is the weakest. In this graph, we have the product of the PV over RT versus the pressure for the nitrogen gas at various temperature. So at lower temperature, the gas particles have insufficient kinetic energy to overcome the intermolecular forces between particles, okay, which results in greater deviation from ideal gas behavior. So for the nitrogen, at the lowest temperature here, 203 Kelvin, it got the largest deviation from the ideal gas. So, to sum up, the real gas will deviate from the ideal gas behavior if the condition of the pressure is very high and also at very low temperature. This is because at the high pressure, the volume of container will decreases. It will make the particles of the gas closer to each other, so we could not neglect the intermolecular forces attraction between the particles, and also the volume of the gas particles will become significant. At low temperature, the kinetic energy of the gas particles decreases, so there is no sufficient kinetic energy to overcome the intermolecular forces attraction. Okay, so the intermolecular forces attraction between particles will become significant. While the condition at which a real gas will behave ideally is at low pressure and also at high temperature.